Hi, everybody. I hope you had a nice weekend. I'm sorry I'm not here today. I'll just be honest and tell you that in my household, we're dealing with some COVID stuff. So I'm not quite sure when I'll be back yet, but I promise I'll be back as soon as I'm able. The good news is your substitute, Mr. Nagel, is awesome. I'm sure he told you he is a retired chemistry teacher. So any of the lessons that I am going to deliver to you through videos like this, he can come over and help you out when you're working on practice or if you have clarification questions. So basically what we're going to do today is we're going to work on that extra page of note packet number 7 that I passed out to you by accident last week. It's a page of notes where it says at the top something about moles of gas at STP to liters of volume conversions. It's like a single two-sided page. There are extras on top of my filing cabinet by the windows if you don't have that. But basically, we're going to fill out that page of notes together today and learn yet another fun mole conversion. Okay, so I am going to do my best to kind of deliver the lesson like I would if I was here in class. The thing is that I have an older Chromebook and there is no stylus for my model of the Chromebook. So I'm going to be using my finger to do all the annotations. So be patient and I promise I'll try my best to write clearly. All right, I'm going to go ahead and share my screen. We're actually not going to start with the notes. We are going to start with a quick review of the mole conversions that we learned last week, and then we will take the notes. We will learn a different path on the mole map. Okay, so these are not the notes. This is not in the notes. So you should just be looking up at the screen right now, paying attention, and just reviewing with me the different conversions with moles that we learned last week. So again, not in the notes, just pay attention. All right, so in the upper right-hand corner of the screen, you'll see the mole map. And that is on an orange sheet of paper that I passed out to you. You're probably gonna wanna take your mole map out at points today. It should be a helpful visual aid for you as you work through now 3 different types of mole conversions. That is after we finish the notes. All right, let's go through the 2 types we already know and then we'll learn the third. All right, so the first review problem says, what is the mass of 2 moles of NaCl? So I gave us 2 moles. We're starting here on the mole map and I would like to know the equivalent mass of those particles in grams. So if you look at your mole map, it says to use the formula mass or the gram formula mass to perform this calculation. So anytime you convert between moles of particles and their equivalent mass in grams, either direction, moles to grams, grams back to moles, step 1 is always going to be to find the GFM, the gram formula mass, which gives you the mass of just 1 mole of particles for a given substance. So how would I find the gram formula mass? Well, I would look at the formula I'm given, which in this case is simple. It's NaCl. And I would note the number of atoms of each element in the formula, such there is 1 Na and 1 Cl. And then I would multiply the numbers of atoms of each element by the atomic mass of that element, which we round to the nearest whole number from the periodic table. So sodium's mass of 22.98977, when rounded to the nearest whole number, is 23. Chlorine's mass of 35.453, when rounded to the nearest whole number, is 35. And when I added that together, the sodium and the chlorine combined, it comes out to 58 grams per mole. Okay, so that's step 1, is to get the GFM, and that tells us the mass in grams per 1 mole of particles of a given substance. So I'm going to clear my annotations, but remember, the first thing I did was to get the gram formula mass. So really what the gram formula a gram formula mass is telling me is this: for every 1 mole of sodium chloride molecules, the equivalent mass of that mole of molecules is 58 grams. So if I was going to convert 2 moles of NaCl to the equivalent mass in grams, some of us might realize that we need to multiply the 2 moles we're given by the 58 grams, which is the mass of just 1 mole of particles. So 2 times 58 will do it. Since there's a lot of conversions, there's 3 total that we're going to know. A lot of us at this point, I have strongly encouraged to use a dimensional analysis setup, which would involve always taking the measurement you're asked to convert. It always goes on the outside of the parentheses with the fraction bar in the middle. If I wanted to cancel out the unit moles, I would place it in the denominator. And the unit I'm converting to, in this case grams, will always go in the numerator. Then I use the relationship from the GFM to fill in the rest. There are 58 grams of mass for every 1 mole of particles of this substance. This setup, 2.0 parenthesis 58 over 1, when plugged into a calculator, basically forces multiplication. Either way you do it, a setup like this, or straight up multiply 2 times 58. The approximate mass of 2 moles of NaCl molecules is 116 grams. Okay, so anytime you go between these 2, moles and grams, when you convert between them, you need the gram formula mass, which gives you the mass of 1 mole of particles of that substance. All right, so we learned that last week. The other conversion we learned is different. We learned how to convert between moles of a substance, moles of particles, to the actual number of particles in the sample. So in the second question, I ask us how many molecules, how many actual molecules are contained in 2 moles of sodium chloride. So really applies to any substance. How many particles, in this case molecules, would be in 2 moles of anything, in this case NaCl. So notice on the mole map, it does not tell me to use the formula mass. It does not tell me to use the GFM. Instead, what it tells me to do is use 6.02 times 10 to the 23rd. So I want to be really clear about that, because anytime you convert between moles and the actual number of particles in the sample, either direction, excuse me, you don't need the GFM. Instead, what you need is this conversion factor, that 1 mole of anything, whether it's 1 mole of molecules of a substance, 1 mole of atoms of an element, 1 mole of donuts, 1 mole of anything equals 6.02 times 10 to the 23rd of that thing, in this case, molecules. So that's the relationship I would need to convert 2 moles of sodium chloride to the actual number of molecules in the sample. Some of us might realize we just need to multiply 2 times 6.02 times 10 to the 23rd. Go for it if you see it and you feel confident about it. But again, for a lot of us, I do recommend a dimensional analysis setup where you take the measurement you're asked to convert, in this case 2 moles. You would always put it on the outside of where the conversion factor is going to go, the parentheses of the fraction bar. Whatever unit I'm converting from is going to go in the denominator always, so I can cancel it. And the unit I want, whoops, in this case, molecules, sorry about that, is going to go up in the numerator. So I would use this relationship to fill in the parentheses, that there are 6.02 times 10 to the 23rd molecules per 1 mole of this substance. This setup essentially, when put into a calculator, forces you to multiply by 2, 2 times 2 parentheses, 6.02 times 10 to the 23rd, divided by 1, close the parentheses. If put in correctly, your calculator should tell you that this is 1.204 times 10 to the 24th. Remember, if your calculator says this, 1.204 E 24, The E means like times 10 to the 24 is the exponent on the power of 10. So that means that. Okay, we have now reviewed what we learned last week, so I would like to transition to that single page of notes that you're going to take with me today. So let's do that. So basically, this is lesson 3, mole conversions part 2, since we already did 2 other mole conversions that we just reviewed last week. Basically, if you have your mole map, what we're going to be doing here is we are going to be, just want to move this, there we go. We're going to be going this direction on the mole map between moles of gas molecules, specifically at STP, to their equivalent volume in liters. And it tells me as a little hint on the mole map to use 22.4 liters. So let's discuss that further. All right, still not in the notes, so bear with me. This guy right here, his portrait may look familiar. That is Avogadro. And we talked about Avogadro in Unit 2. We did properties of gases and gas laws. Because Avogadro is the scientist that said this. He said when you have different samples of gas, like say helium, nitrogen, or methane, if you say had those 3 samples of gas and they occupied the same volume, so they took up the same amount of space, they were held at the same pressure, and they were held at the same temperature. If those 3 things were the same, the volume, pressure, and temperature of the gas, regardless of the identity of the gas, those gas samples would contain the same number of molecules. So this guy, Avogadro, is the scientist that came up with that. So he came up with that through experiments. And he actually was able to take it one step further. When we started this unit, we called the number the mole, 6.02 times 10 to the 23rd. Another name for that is Avogadro's number. And this is why. Avogadro basically came up with the concept of the mole, and in addition was able to say this. He was able to say, okay, if you have a mole of gas molecules, 6.02 times 10 to the 23rd of them, and those gas molecules are at STP, that 1 mole of gas molecules of any gas are at STP, and those gas molecules have the same temperature and the same pressure, that 1 mole of gas molecules is going to occupy 22.4 liters of space. Okay, so basically that's where the overall relationship we're about to discuss, 1 mole of gas particles at STP occupies 22.4 liters of volume. That's where that comes from. Oops. Did I make this? There we go. All right, so here's the notes, finally. So basically where we're going today is here. We're saying if we have 1 mole of any gas, particularly if that gas is at standard temperature and pressure, that gas will occupy exactly 22.4 liters of volume. So 1 mole of any gas at STP takes up 22.4 liters of space. Okay, so then we said that. All right, so a sample problem. Let's say I wanted to convert 4.5 moles of carbon dioxide gas to liters if the gas was at standard temperature and pressure. All right, so it doesn't really matter that it's carbon dioxide gas, as long as I see whatever gas in the problem is at STP, and I know I'm going to convert between moles of that gas to their equivalent liters in volume, I can use this relationship. So a dimensional analysis setup works well here. And if you see that you really just need to multiply 4.5 times 22.4, that works too. But a dimensional analysis setup would look like this. 4.5 moles. What I'm asked to convert outside the parentheses, put the parentheses up, fraction bar in the middle. The unit I'm getting rid of, moles in this case, would go in the denominator. The unit I want, which is liters of gas, would go in the numerator. I use this relationship to fill in the rest, that there are 22.4 liters of volume per every 1 mole of gas molecules at STP. Basically 4.5 parenthesis 22.4 over 1, close the parentheses in your calculator, or just straight up multiplying 4.5 times 22.4. The equivalent volume of that 4.5 moles of gas is 100.8 liters. All right, so it's really not different than what we did last week in terms of like how one would calculate it. It's just a different conversion factor we're using to do that calculation. All right, so on the very back page, well, the back of that extra page I gave you last week, you'll see these two let's practice problems. I quickly am going to run through them, and then you're going to try a formative that puts all of the conversions together. So look forward to that. All right, here we go. How many moles are present in 5 liters of carbon monoxide gas at STP? As soon as we see that the gas is at STP, we know we can convert the moles of gas to liters using the relationship that 1 mole of any gas at STP occupies 22.4 liters of volume. In this case, I'm going to convert liters to moles, the opposite of what I just did. You might realize you need to divide the 5 liters by 22.4. If not, use a dimensional analysis setup. The liters would go on the bottom. What I want, in this case, the moles would go up top. For every 1 mole of gas at STP, there are 22.4 liters of volume. 5 parenthesis 1 over 24, close the parentheses, or 5 divided by 22.4. This comes out to be 0.2 when rounded to the tenths, or 223 when rounded to the thousandths. Oh, excuse me, moles of particles. So a little less than 1/4 of a mole of particles is equivalent to 5 liters of gas. That's how much space that would take up at STP. Okay, so it's basically what we just did in the notes, but opposite direction. So let's do one more, and then you're going to try that practice formative. All right, so this time I want to know how many liters of volume 0.5 moles of water vapor would occupy at standard temperature and pressure. Again, as soon as I see the gas is at STP, I know I can use the relationship that 1 mole of gas at STP, any gas, occupies 22.4 liters of space. In this case, if you see that you just need to multiply 0.5 moles times 22.4, go for it. I would encourage, though, for most of us, a dimensional analysis setup where we would take the moles we're given in the problem, put them on the outside. The unit moles would go in the denominator this time, so it cancels. I want liters of volume. That would go in the numerator. I use this relationship that there are 22.4 liters of volume for every 1 mole of gas at standard temperature and pressure. When converted properly in a calculator, that 1/2 mole of gas particles would occupy 11.2 liters of space. Okay, that is the idea. Oops. Sorry, I just realized that I probably should leave that up there a little bit longer. So that is the idea. Where we're going next is to the mixed moles practice formative that's posted on your Google Classroom. So here's the deal. This formative is kind of structured so that at first, each of the like mole conversions are together. So the mole to mass conversions where you use the GFM as your conversion factor, those are together. The moles to particle conversions where you use 1 mole equals 6.02 times 10 to the 23rd particles are together. And then this, what we just learned, the moles of gas at STP to their liter of volume are all together. But then when you hit part 4, that is when the fun really starts, because then they're all mixed together. So you're going to have to figure out, I would say, using your mole map, take it out, it's helpful. figure out how to convert between the various units, like what conversion factor you need. Do I need the GFM? Do I need 6.02? Do I need the 22.4 liters? And then go ahead and try to do the conversion. Remember what I said, Mr. Nagel, he knows his stuff. He can help you, so please don't hesitate to reach out to him. Ask him if you need a little assistance setting one of these up. And just do your best. You have to show some work. I'm not going to give you credit if you don't show me roughly how you're getting the answers. You do not have to use dimensional analysis, but I need to see somehow how you're arriving at the correct answers. All right. I know you can do this. Take your time. Ask for help if you need it. And hopefully I'll see you soon. All right. Bye, everybody. Good luck.